The vast majority of you were able to jump right into this and get an answer pretty quickly. Some of you are still struggling. Of course, some of you weren't here yesterday. So I'm not going to spend a lot of time uh, explaining all the little things. If you need the little things explained, well, I'd say something rude like come to school, but practice. That'll make a difference. But also take a look at what we did yesterday. First, when I look at this problem, I hope that you see that you can break this up into 3 smaller diagrams, and that's what I expect you to be able to do. So I expect you to say, okay, I've got 180 newtons this way and T1 this way. And yes, there should be some up and down forces here. But without friction in this problem, I think we can ignore the up and down forces since it's not accelerating that way. You should probably draw them in for practice. I'm seeing that there's probably 2 forces here, T1 and T2. And then the last one, just T2. Like any of these problems, we're just drawing a free body diagram, identifying the forces acting in the system, and deciding whether to apply to Newton's first law or Newton's second law. In this problem, it's Newton's second law problem. So each one of these is going to experience an acceleration. For those of you who weren't here yesterday, the important distinction is that they all have to experience the same acceleration. That makes a difference. If you don't know that, you can't solve the problem. But they all have to accelerate the same, or the couplings are breaking. So that means that I have 180 minus T1 equals 10A. Applying Newton's second law, adding up the forces acting on the object, set it equal to ma. And then T1 minus T2 equals 20A. It's the middle car. 2 forces acting on it. And last, T2 equals 30A. Each one of these, net force equals ma. Now, you've got 3 equations and 3 unknowns. Your job is to identify an answer from here. And unfortunately for you, probably the best way to get that answer, and this will be true all the time, so even if you didn't write this down yesterday and were here, it's almost always going to be easier to find the acceleration first. So I would encourage you to do that. It will be hardest to try and eliminate acceleration. In fact, it might be almost impossible. So find acceleration first. It's usually best to substitute into the middle object. It'll have all the things in it. It'll have both of the variables because it's got the 2 unknowns. We refer to the tensions in this problem as internal forces. Ultimately, there's an external force of 180 newtons working on the whole train. The internal forces may or may not be all that important. You're asked to find them, though, so we need to identify them. So I'm going to do the substitutions here. I have to solve this for T1, and I'm kind of done explaining algebra, but I will if I have to. I expect you guys to be able to do algebra. It might take you extra steps, that's fine. But when it comes to substitution, that's T1. That's T2. And there, all my substitution is done. I've got a single equation now with just acceleration in it. I would like you to see something, so move everything with acceleration to the same side, which is what you would have to do anyways. So I get 180 equals 10A plus 20A plus 30A. It is important that you see that you can factor out the A's. And that what you get here tells you whether you've done this right or not. This tells you whether you've done all of your work right. You should see all of the masses of your system summed together. If you don't see that, you've made a mistake, because this is the inertia of the system. Since every part of your system is going to be accelerating at the same rate, the inertia of the system determines the acceleration. In fact, when you're done with this correctly, you should get a version of Newton's second law. which is what we have here. We have 180, which is the net force on the system. We have the sum of all the masses, which is the inertia of the system. And then we have the acceleration of the system. You should get Newton's second law for the system. It's kind of like what would happen if instead of having 3 boxes, I have just 1 box that's 60 kilograms. The way the box behaves will be the same. In fact, you could probably use that to your advantage and not do all of those individual things and find the acceleration in a single step. Either way, if you've been doing this problem, you know that the acceleration of the system ends up being 3. We take that 60 kilograms, put it under 180, and we get an acceleration of 3 meters per second squared. This is not what you're asked to find, but it will tell you the answer now. If you want tension 2, that's right here. Plug in your 3 and I'll give you tension 2. If you want tension 1, probably right here. That'll probably do it. And let's see, tension 2 comes out to be 90 newtons. And tension 1 comes out to be 150 newtons. Pretty straightforward, I think. So since it is straightforward, and since body language is something, you have, I'll go with 4 minutes for me to be able to call any one of you out to tell me how this changes when I pull on this side instead. And I know exactly who I'm calling on. All right. So, West, how does the acceleration of the system change? It doesn't. That's right. It's still 3 meters per second squared. Right. The whole thing is still 60 kilograms. It's still being pulled with 180 Newton force. The only difference is that's going to the left now, not the right. Any question about that? Now, you could have done it the long way, but that has to be true still. And it has to still be true that T1 equals 10A. There's only one force acting on the last train car. And of course, 180 minus T2 has to be equal to 30A. That's the forces acting on the first train car. I know the acceleration now, so I really don't need anything about the middle car. Folks, if you didn't know to do this, even though I tried to make that clear, perhaps write something down right now. It'll help you the next time. That if the conditions don't change and you're just changing sides, also, you can always treat it like a system, especially if there's no friction. Treating it like a system is like treating it like it's one box with the mass of all of the objects. Let's face it, the 180 Newton force doesn't know that it's pulling on 3 different boxes. It's just pulling on the inertia of 60 kilograms. Either way, that gives you that T1 is now 30 newtons, and T2 didn't change, it's 90 newtons.
I got the answers for T1 and T2, but I got like -3 for acceleration.
So you chose left to be negative, okay. I would not do that from now on. I would consider that, say, your positive direction, always the direction of the acceleration. You'll be happier, but it's not really any different. Now, there are some things here that you should notice, and it's the kind of questions that come up on the test where you have to write something in paragraph form that you guys are sometimes not particularly well adapted to do. And let's think about it for just a minute. Each of the couplings has to pull the train cars that are behind them. That's why this coupling didn't change. Whether I pulled from the left or pulled from the right, it was always pulling 30 kilograms of mass. Do you guys see that? So that's why the tension in that coupling never changed, because it was always pulling the same amount. This coupling, however, changed drastically. When I pulled to the right, it had to pull 50 kilograms of mass. When I pulled to the left, it only had to pull 10 kilograms of mass. Now, if you're trying to preserve your equipment and trying to make sure it will last for as long amount of time as possible, then putting your train cars in one order can make a big difference than putting it in another order. If you're trying to reduce the tension on the couplings, then you'd pull them with the lightest cars at the end and the heaviest cars at the front instead of the reverse, which is what they do. Train problems aren't that interesting. At least what I mean by that is once you've gotten the hang of it, they're all the same. It's just different masses, different boxes, more numbers of boxes. Keep in mind one thing. Now that you know a couple of secrets, like the fact that you could probably add up all the mass and treat it like a single object, then there could be 100 train cars, right? You don't have to actually look at each individual train car. You could treat them like a bunch. In fact, you could also always treat your system in parts. Like maybe there's just two boxes here. One that's got a mass of 30 kilograms. The other one has a mass of 30 kilograms. You can treat it like that. There's nothing wrong with that. Or, you could break it up a different way. Combine these together. And these are 50. So having 100 boxes doesn't really change the problem. You can still break it up into just maybe one or two sections if you need to. The next thing, and you should practice this at home, because I don't want to do it here. You should put a coefficient here and see what happens. In fact, I would like you to do this problem for homework. Treat it with coefficient of friction and see how it affects your answer. I can think we all agree it's no longer going to be 3 any longer. It's going to have a different acceleration. It's going to be less because we have friction acting in the system. And you are likely going to have to now take into account the y direction. So this is a more complicated question. And if you don't want to do it for 3 boxes, then knock away the 10 kilogram box and do it just for 2. Okay? If you think you've got it nailed, try it for 3 boxes. But if you don't, try it just for 2. We're not going to stay there. We're going to try something. We're going to look at something else. That was homework. Okay? So we're going to add something to today first. So for a modified Atwood machine, generally the way I draw it is pretty straightforward. I usually use put the floor in here, and then I'll put a table. That's not a table. There's a table. And then the box on the table, a pulley, and then the box hanging off the table. No, box hanging off the table. There we go. There we go. Our modified Atwood machine question. They just love these questions. Me, I'm ambivalent about them. They're just okay. We're going to say that this one is 10 kilograms. Actually, no, let's just do M2 and M1. Now, the Atwood machine question is used a lot because there's lots of variation, and every little variation adds a different subtlety. So let me just be really, really clear from the beginning. we're dealing with a super simplified version of the modified Atwood machine. We're going to start with no friction, because you guys understand friction plays a role here too. We're going to start with massless thread or string. They can add mass, they do. And a massless pulley with no friction. So you understand that each one of these modifications is a way in which they can change the problem on the actual exam. Do you guys see that? So having thread that has mass means that the more the system moves, the more weight is hanging off the edge, the more it pulls on the mass. That's a change. Pulleys with mass, they add inertia to the system. They slow the system down. For the most part, if you can understand the basic system, you're very likely to understand the others. So let's start with some of the basic rules of an Atwood machine. First, all Atwood machines are going to have a pulley, and the pulley is going to redirect the force. That is what pulleys do. They redirect force. So the next statement, though, is good, is really valuable to me, which is why I'm stopping, because all the people without pencils should get one. The tension in a pulley, the tension in the string around a pulley will be the same everywhere on the string. The tension in the string around a pulley will be the same everywhere on the string. Now, in all caps, if the pulley has no mass. That's a big if. If the pulley has mass, that's not true. The tension's different on either side of the pulley. But if the pulley is massless, then the tension is everywhere the same in the string. Which means, in this example, the tension pulling this way on box 1 will have to be the same as the tension pulling this way on box 2. The first misconception is that when I put no friction here, there are people in the room who think there's no tension in the string and the box will just fall because there's nothing to hold it in place. The box will fall, but there'll be tension in the string. There's tension because box 1 has inertia. It doesn't want to move. And because it doesn't want to move, it will take an unbalanced force to move it. That creates tension in the string. That slows down this box. So box 2 doesn't fall just straight down. It accelerates, but it doesn't accelerate at G. It's slower than that. And the more inertia this box has, the slower box 2 falls. These are studies in inertia. They always are. And they're trying to trip you up. So, free body diagram for this problem starts out with clearly M2, G, and tension. I think it should be clear that if there's no friction on the table, the system is going to accelerate, but the tension should be less than the weight. That doesn't seem unreasonable to me, but make sure you understand that. On block 1, I'm going to make every reasonable effort to make sure to draw the tension that is sideways the same length as the tension that was upwards. Now, yeah, there's going to be M1G and normal. Now, here's the next thing. Our objects are both accelerating in different directions. How are we going to handle that when it comes to the sign of the acceleration? One accelerates down, one accelerates to the side. I handle this different than your textbook. So I'm going to give you one method. Your textbook will give you another method. If you want the textbook method, fine, you'll get the right answer. If you use my method, you'll get the right answer. You choose the method you like best. I am not going to explain the textbook method. I think it's more complicated, but I'm going to explain my method, okay? My method is to merely decide the direction you want to be positive for both objects and make them both positive. Meaning, I think the system is going to go in this direction. Don't you think it's going to go in that direction? So I'm going to make this direction positive. I'm putting the arrow around the pulley because that tells me both that the box on the table is going to go to the right, and that's positive, and the box that is hanging is going to go down, and that's positive. I am assigning direction to both objects at once. Your book does this different. And so if you like the book's way, great. I don't. I think that makes the most sense. Now, from this point, your problem is no different than what we've already done. This becomes a Newton's second law problem with M2G minus tension equals M2A. Net force equals MA. Do I need to explain that? Because I will. Okay. So then tension equals M1A. Good there? If not, I'll explain it. Just looking at this picture, there's one unbalanced force to the right that accelerates M1. And looking at this picture, two forces, they're unbalanced, that accelerates M2. Now, we've been doing this kind of problem. We've got the end of our Newton's laws. They generated two relationships. What are you likely to do? Find something. You can find a force or you can find an acceleration. As I said to you before, finding a acceleration is probably the easiest thing to do. So that's what I'm going to do. I'm going to substitute in for tension. And I'll get M2G minus M1A equals M2A. M2G equals M1A plus M2A. Are we keeping up? Because I'm going to stop right here. And remind you that if you do a Newton's third law problem correctly, a multi-body problem, then eventually you should see the sum of all the masses. More than that, do you see that it's the mass that's hung that causes the system to move? That's the external force, is the weight that was hung off the system. This is the inertia of the system. And therefore, this is the acceleration of the system. When you're done with one of these problems, you should see net force equals MA as part of your response. That'll show up at the end of the question. This idea that Newton's second law is going to be embedded in all the problems that we do. So this is the mass of the system. Unbalanced force. You'll always show up. So if you get a sign wrong, you'll know it there. You'll get a negative sign where it's not supposed to be, and you'll know to go back and look. There should always be a point where you're adding it all together. This is the modified Atwood. And obviously, I'm going to be showing you many examples of this just to make sure we nail it. But modifying it means putting it on a ramp, putting both sides on a ramp. Who knows? There's all sorts of modifications here. We'll move on to another example, okay? It would be best if before you walk out the door, we take a look at the actual Atwood machine. I make the pulley really big when I do these because I want you to I want to separate the masses out so you can kind of individually see them easier. But actual pulleys tend to not be very big like this. Also, I am carefully trying to draw the boxes to represent different sizes so that the bigger boxes for the time being are heavier box. And I'll label this M1 and M2. Okay. Now, this is where I really want you to pay attention. Draw the free body diagram here. If you want a hint, draw tension first on both. Now, this is the kind of problem where the size of the arrows will be tested on your exam. They've done it a bunch of times. They'll put this on a grid and they will make sure that your arrow sizes all work out. When you drew the tensions, did you take special care to make sure that both arrows were drawn upwards and the same size? They should be. Tension is the same everywhere in the string if the pulley is massless, and we're dealing with massless pulleys. Now, is there any doubt which direction the system is going to accelerate? Can we all wrap our heads around the idea that it's likely that this is going to be the direction the system will go? The only way that can happen is if the net force on the left is unbalanced downwards, and the net force on the right has to be unbalanced upwards. It's the only way the system will accelerate like this. So the tension is got to be greater than the weight of M1, but less than the weight of M2. It has to be, or else this won't work. That's why these are studies in inertia. They force you to really think about the size of the forces acting on the individual objects. Now, it shouldn't be too much work for us to consider what Newton's second law should look like for each of these masses. Right, net force. I'm choosing downwards to be positive on mass 1 because it's going to accelerate downwards. So M1G downwards minus tension upwards equals MA. Can we do that for the other mass? Be careful, for the other mass, positive is upwards. So tension minus M2G equals M2A. Good so far? Got 1 minute or so left to show you this. So M1G minus tension equals M1A. T minus M2G equals M2A. I just wrote them down there. Is that okay? If I add these two equations together, the right side gives me M1A plus M2A. Do you see that the T's cancel on the left side? So I have a positive T and a negative T. Now, this shouldn't be a terrible surprise, but every year I have students who just, I don't know. I'm going to do one more thing, and that's just a factor. If you've done it correctly, you'll see the sum of the masses. Bless you. You'll see the sum of the masses here. You'll see the acceleration, and you'll see the net force, right? Gravity pulled down on both objects. One of them was bigger than the other. These aren't terribly hard, but there's so many things to look at.